In this example, we're asked to look at a system which is made up of this rigid bar AF pinned to ground at C. End A, there's a thin rod which connects point A back to ground there at B. We'll call that segment 1. And on the right-hand side, there's a column that's immediately below D. Initially, there's a clearance gap of delta between the top of that column and D before a force is applied. However, when a force P is applied, we're asked to find two things. One is, if that force P is just enough to close the gap there at D, what's the strain in rod AB in segment 1? Part B, if we now double that load P, what we had in A, what's the corresponding strain in segment 2? Before we start, I do want to say that I failed to write down a couple pieces of important information. Assume that we know the Young's modulus for both the thin rod and the column, as well as the cross-sectional area of the two. So we know E1 and A1, we know E2 and A2. First thing we're going to do is look at kinematics. We're going to look at the rotation of bar AF, shown by a rotation angle there of theta. I'm going to denote the distance that A has moved up as delta 1. That's the amount of stretch in segment 1. And delta 2 represents the motion down for D, which is the compression of element 2. So the problem says that we can assume we have small rotations. So for trig, for small angles of rotation, two things we can say. The rotation angle is approximately equal to the inverse tan of delta 1 over 2D. And for small angles, this is approximately equal to the angle itself. So that's delta 1 divided by 2D. Also, if we look over at the right-hand side, the same angle is related back to the movement there of D, which is delta 2, divided by the distance between O and D. That's 3D. Again, for small angles, delta 2 divided by 3D. So therefore, from this, with these two angles being the same, what we have is the ratio of delta 1 to 2D is equal to the ratio of delta 2 to 3D. So from this, we say that for any rotation of that bar, the stretch or compression for segment 1, delta 1, is 2/3 of the stretch or compression there for column 2 once the bar is in contact with that bar. So what we have here is that for part A, we know that we've just closed the gap, so there's no actual compression of the rod. So delta 2, that is the initial gap. So from that, I can say that the strain in segment 1 is given by the amount of stretch, delta 1, divided by the length of that, which is 4D. And since delta 1 is equal to 2/3 of delta 2, which is equal to 2/3 of delta, this ends up being delta over 6D. So the answer to the first part is strictly from kinematics. How much strain is put into segment 1 just to get the bar to close the gap? Now for part B, we're going to have to deal with forces. So what I'm going to do is go back up to my bar. I'm going to draw the FBD. For the FBD, I'm going to have this force, which will be the load that's carried by member 1. I'll call that F1. So that's an equal and opposite force there on 1. So the FBD for segment 1 looks like this. And then for the bar, once it's in contact with the column will be putting a force of F2 back on the bar, equal and opposite force then on the column itself. Obviously, segment 2 is in compression, segment 1 is in extension. Based on the FBD, I'll do a summation of moments about the pin joint there of O. That's F1, which has a moment arm of 2D. It's a plus because it's in the counterclockwise direction. I have F2. That has a moment arm of 3D. It's also a plus moment about O. And then P has a moment arm of 5D. It's in a clockwise direction. So there's a negative sign. And for equilibrium, that's equal to a 0. So from this, we see that 2F1 plus 3F2 is equal to 5 times the applied force P. Recall for part A, what we wanted to have was it just in contact with column 2. In other words, F2 is a 0. What this says then is that the load that we need for part A is simply then 2/5 of F1. F1, we know, is equal to sigma 1 times A1, the stress in 1 times the cross-sectional area of 1. And we know that this is equal to 2/5. Sigma 1 is E1 times epsilon 1, so this becomes E1 A1 epsilon 1. And from this, we have an answer because we are given E1 A1. We found epsilon 1 back up here in part A. Now let's move on to part B. For part B, F2 is not a 0, and we're also looking for the case where the load has been doubled from what it was there on A. So we have a number for that because it's twice that number there. Going back up to our equilibrium equation, we have 2F1 plus 3F2 is equal to 5 times the number we get there for PB. So I put in F1 is equal to sigma 1 A1. I put in sigma 2 A2 for F2. And then for sigma 1, we know that's E1 epsilon 1, so this becomes 2 E1 A1 epsilon 1 plus 3 E2 A2 epsilon 2. And finally, we know that the relationship between epsilon and the strain, well, the strain is equal to the delta divided by the length. So this becomes 2 E1 A1 divided by the length of segment 1 times delta 1. Same kind of thing for 2. 3 E2 A2 divided by length of 2 times delta 2 is therefore equal to 5 times the load PB. Keep in mind that our kinematics told us above that delta 1 is 2/3 of delta 2. I take that expression and I get that the delta 2, if I just solve that equation for delta 2, I get 5 P sub B divided by 4/3 E1 A1 divided by the length of 1 plus 3 E2 A2 divided by L2, and we get a number because we've got everything that we need to solve for there. So therefore from this then the strain into is the stretch, the amount of stretch we have divided by the length. So this becomes delta 2, I think L2 is equal to 3D. So we put in those numbers and we have that. So in the first part was just kinematics. What's the strain that exists in segment 1 when that bar rotates through just enough of an angle that close that gap over there at D. Part B, we have to bring in the forces because, one, we need to know how much force that it took in part A to close the gap. We double that, and then from that we can get the relationship between the forces and the applied force. We relate the forces back to the stresses back to the strains, as in this equation here. We relate the strains back to the elongation, and then from that we can solve for delta 2 and therefore epsilon 2.